This video begins our introduction to exponents, and first we are going to just review what that 5 to the second means. It means to multiply the 5 by itself the number of times in the exponent. So 5 times 5 is 25. The 5 is called the base. Now if we use variables for repeated multiplication, x times x, it becomes x to the second power. But be careful, if we are adding x's, we don't get exponents, we get twice x. This leads us to the first basic rule with exponents called the product rule. You keep the common base, which up here was the x, and then add the exponents. So here up top we had 1 and 1, which added to the 2. In general terms, x to the a times x to the b equals x to the a plus b. First example, x to the 7th times x. There's a 1 up here, so we're adding 7 plus 1 and we'll get x to the 8th. If you need to see this expanded out to understand why we get the 8, x to the 7th is in the green here. 1, 2, 3, 4, 5, 6, 7 x's. And then the black one is the extra x. Altogether you have 8 repeated x's. Second example, x to the 7th times x to the 4th. So we are going to have all 7 x's written out times 4 more of them. That's why we are adding up the exponents, so x to the 11th. Here's a problem where our base is a number. We are still going to keep the base, which is 4, and add the exponents. So we will have 4 to the 7th power. If you need to see this written out, 4 to the 3rd is here in the green, 4 to the 4th is here in the blue. You can see there are 7 4s, so 4 to the 7th. I want you to notice that you do not get 16 to the 7th power. 16 to the 7th power would mean 16 in all of these spots. And we multiply that out, it would be a huge number. If you do multiply all these 4s out, you would get 16,384. But in this unit we are looking to leave things in exponent form, so we are looking to leave it as 4 to the 7th. If a problem says to evaluate, then you'd put the 16,384. Example 4 is negative 3x to the 6th times 4x to the 5th. We are going to multiply the coefficients, so negative 12, and we are multiplying our x's, which means we're adding these exponents. So we will get negative 12x to the 11th. Because this is a multiplication, we can change the order around. So if you need to see what's happening here, then we can put the negative 3 times the 4 out front, and then the x's next to each other here. And this shows we're doing the product rule where we add the exponents. Next here we are going to compare two problems that look very much the same. A squared times 5a versus a squared plus 5a. With multiplication we can multiply anything we want. We do not need like terms. So here the 5 will be in front, and then a squared times a brings you to a to the 3rd because we're going to add the 2 into the 1 extra. So we have 5a to the 3rd. This one over here, now we're adding, and in order to add we have to have like terms. The 5a would have to have a squared on it in order to be a like term here. So there's nothing we can do here. Next problem, negative 5mn times itself, negative 5mn. That means we are squaring something because we're multiplying it by itself. So negative 5 times negative 5 will be 25. M times m is m to the 2nd power. N times n is n to the second power. This is the last example in the product rule group. 8xy to the fourth times negative x to the sixth y to the squared. Without showing any work, we are going to get 8 times negative 1, so it will be negative 8. X times x to the sixth, we'll bring that up to x to the seventh. Y to the fourth times y to the second. We'll add those exponents and get y to the sixth. If you need to see this written out a little bit more in detail, I will do that. So here I put the coefficients 8 and then times the negative 1 here, x to the sixth here, y the fourth, y the second here. And this is where we add exponents as we did in the introductory problems number 1 and 2. So x to the seventh, y to the sixth. Next type of exponent problem involves fractions, which really is called the division rule. X to the a over x to the b equals x to the a minus b. So we will be subtracting exponents, and I will explain why. The other form of this, x to the a over x to the b, if we decide to start the subtraction from down here in the bottom, we would do b minus a. So because you start the subtraction in the bottom, the variable goes in the bottom, and we put a 1 up top. So we are still going to keep the common base, but subtract the exponents when we are talking about fractions. The other big point here is throughout the rest of this course, with one exception later on, there are to be no negative exponents in your answers. First example here, x to the seventh over x to the second. If we expand this all out, we have 1, 2, 3, 4, 5, 6, 7 x's on top and 2 on the bottom. These 2 on the bottom will divide out with 2 on the top. Because we're talking about multiplication, we can do that. So here, the 2 x's are canceling out, dividing out with 2 of them on the top, leaving us with 1, 2, 3, 4, 5 left over, so x to the fifth. This is coming from taking the 7 minus the 2. Okay, so here we're talking about subtraction. Here we are going to do the same problem as number 1, but just reversed. X to the second is up top and x to the seventh is in the bottom. As we start the exponent unit, I am expanding things out, but in the future we will not want to do this. Here we have 2 x's on the top and 7 on the bottom. And again, we are going to take the 2 up here and cancel out with 2 on the bottom. So here we took the 2 of them and canceled out with 2 of them. Now, when we cancel things out in fractions, we should put 1s in their places. I did not show that up here, so I just put it in now. But when the 1 is in the denominator, we don't need to show it in our answer. Down here, our 1 is in the numerator. So we need to keep that in our answer, and we've got the 5 x's left over in the denominator, so our answer is 1 over x to the fifth. So again, our answer did come from doing keeping the base x and subtracting 7 minus 2, but this time the 7 was in the denominator. The larger exponent was down here. So because we start the subtraction in the denominator, your answer needs to go in the denominator. I do want to talk about the other method you could do on this problem. If we start our subtraction from the top number and do 2 minus 7, so 2 minus 7, we would get x to the negative fifth. And because we started our subtraction in the top, this would be a top answer. but we are not allowed to use any negative exponents in our answers. So this would not be acceptable. This form is what we need here. Problem 3, m to the 100th over m to the 100th. We have talked about this stuff before, but maybe not just with a large exponent. This will equal 1, because anything divided by itself is always 1. But if you expand all of this out, you'd have a 100 of the m's, and you'd have 100 of the m's. Every single one would cancel out and leave us with a 1 in all of the places. So essentially we would have 1 over 1, which does give us 1. Here's a problem. I'll take a moment to write this down. This is a combination of the previous problems. We just have x's and y's. So we're going to take this problem and separate it into the fraction part with the numbers, the x's and the y's. Some students find it helpful to separate the parts of this. So we are going to reduce 3 over 21 like it's its own little fraction. They can both divide by 3, so we will have 1/7. Looking at the x's, we are going to do 8 minus 2 and get x to the 6th. So we will get x to the 6th, and it will be on the top when we write our final answer. For the y variables, the bigger exponent is down on the bottom here. So we're going to do 12 minus 3, which will leave us with y to the 9th on the bottom. So writing all of this out now, we have the 1/7, x to the 6th on top, y to the 9th on the bottom. And because we have an x to the 6th up here, we really don't need to write the 1, so the best answer is right here. Last problem in this group, -5mn to the 3rd over 20m to the 2nd n to the 6th. Looking at this quickly, we reduce the 5/20ths, so that will give us -1/4. M over m squared, we will take the top one away from the bottom and leave us with a single m on the denominator. And here the bigger n exponent is in the denominator as well, so we will do the 6 minus the 3, which will leave us with n to the 3rd in the bottom. So again, splitting this apart into the different parts, the 5 over 20 can reduce by 5. And here we will subtract 2 minus 1, leaving us with m in the denominator. And same thing here, we're starting with the 6 minus 3, so we will have n to the 3rd in the bottom. So here's our final answer there. In this case, we do need the 1 up here in the numerator because there's no variables to go with it. The next part of the exponents we're talking about is the 0 exponent rule. Any base to the 0 exponent is 1. X to the 0 exponent will equal 1. Just a number like 15 to the 0 exponent will equal 1. And I will explain why. Because let's take x to the 3rd over x to the 3rd and look at solving it two different ways. This first method, we are going to expand it out. So we have xxx on top, xxx on the bottom. In this case, we're going to cancel all 3 on top out with all 3 on the bottom and put 1s in their places. So we have 1 over 1, which results in 1. This first method was basically indicating that anything over itself will give you 1. This other side, we're going to use the subtraction rule because we do have a division problem. So we will get x to the 3 minus 3, which will be 0. So here we're subtracting the exponents, which gives us x to the 0. This is 2 legitimate ways of doing the same problem, and it gives us a little proof. It shows that a base to the 0 exponent equals 1. Just 3 examples here for this. First one, 8m to the 0. The 0 exponent only goes with the base m, so it's this part here that becomes 1. The 8 will remain. So this part became 1. The 8 stays. 8 times 1 gives us 8. Problem 2, 8m to the 6th n to the 0. Only the n to the 0 will become 1, and the 8m to the 6th will remain. Here we have negative 8, and ABC is to the 0 power. So this 0 power goes with the entire parenthesis part here. So this makes this entire chunk equal to 1, and the negative 8 will remain out front. So negative 8 times 1 leaves us with negative 8. The next rule with the exponents we'll talk about is the power rule, where you have a base to a power, but you have that in parentheses to another power outside. So we have multiple powers. In this case, you're going to keep the base, but multiply the exponents. And I'll give an example here to show why. Let's take x to the 5th and the whole thing to the 2nd power. To explain how this works, this exponent 2 outside means to take the inside and multiply itself by itself twice. So we have x to the 5th times x to the 5th. This is our basic exponent rule where we add the exponents that we talked about at the beginning. So we get x to the 10th. Notice here that you do not get x to the 25th. We're not doing just a regular number 5 times itself. We're doing exponents, so we're adding. And you can see we get x to the 10th. The shortcut here is to simply multiply these two exponents together. So in the future, I would expect that you would just be able to go directly from here out to the x to the 10th. But if it's helpful for you to rewrite the problem out twice, that's fine as well. A couple examples for the power rule. Number 1, x to the 6th to the 3rd power. We are going to just multiply these exponents because we have 3 groups of x to the 6th. So this is going to equal x to the 18th. The other reason you can show to get x to the 18th is to take the x to the 6th and multiply it by itself 3 times. x6, x6, x6. This is a case where we add exponents. So we're doing 3 groups of 6. 6 times 3 is 18. Here we are looking at a problem with a single term on the inside, negative 6a, and a single power on the outside. This exponent on the outside applies to each part on the inside because we have a product. So we write the negative 6, which has to be in parentheses because it's inside the parentheses here, to the 4th power, and the a goes to the 4th power. And we need to work this out here. You can use your calculator with the exponent key, but I will show it longhand. Negative 6 to the 4th is negative 6 times itself 4 times. The first pair is 36. Bring down your multiplication. The second pair is 36. 36 times 36 is 1296. 1296. And when you just have a variable to an exponent, it just stays a to the 4th power. This is the last section of this video. Exponents and fractions. Negative 5 over a, all in parentheses, to the 4th power. This outside exponent applies to both the numerator and denominator in this fraction. So we have negative 5 to the 4th power, and that will have to be written in parentheses. And we also have a to the 4th power. So we need to multiply negative 5 by itself 4 times. First pair is positive 25, second pair positive 25, multiply 625. So we have 625 in the numerator, and a to the 4th just stays a to the 4th in the denominator. Last problem. Negative 4m over n, all in parentheses to the 3rd power. So the exponent goes with everything inside. Negative 4 in parentheses to the 3rd power, m to the 3rd power, and the n to the 3rd power. So we'll do this work for the negative 4 off to the side. So here we're multiplying negative 4 by itself 3 times. Negative 4, negative 4, negative 4. The first pair will give you positive 16 times, break down your times sign, and the negative 4. 16 times 4 is 64, but a positive times a negative is negative. So when you have the odd number of negatives in multiplication, you will remain negative. So negative 64, m stays to the 3rd power, and then n to the 3rd power, and that's our final answer.